if I have a 9, I get up at like 9:40 or 8:40, so I still have enough time to do it somehow. I mean, like, you just throw the water and hit go, and then while it's brewing, you just do whatever else you would normally do.
Yeah, I'm just not like that.
Yeah, I find time for it, I guess. I need it. I need it, so.
You make coffee?
Yeah. It's alright. One off. Yeah, that was pretty rough, but other than that.
I was struggling.
Wish we got that. Yeah. I'm not hard.
Okay, you guys are doing okay? The weekend was okay too?
Something.
Okay.
95 degrees. It was what? 93 and 90% humidity. It was pretty 70 for us. Yeah, that would have been enjoyable.
You guys played soccer in that weather?
Yeah.
And we got back.
No, I got practice. It's our one day off. We were supposed to, but like NCAA rules, so you have to have one day off for like straight week.
Okay, so last time we ended with composition of functions, so let me start from there again. So let's let f and g be functions. The composition of f and g is given by f circle g. That's the notation we use for the composition of the two functions. And whenever you define a new function, you have to say what it does to an input. So what does it do to x? Well, it computes g of x first, and then whatever g of x is, it applies f to that. And that's the definition of the composition function. So what's happening then is that you start with an x in the domain of g, you apply g to x, you obtain some number y, and then once you obtain y, you apply f to it to obtain some number z, and z will be in the range of f. Right? So the composition function takes you from the domain of g into the range of f, in fact. So this is what the composition of f and g does. So so g takes x to y, f takes y to z, then the composition takes x all the way to z. Okay. Is everybody clear with that? Okay. So a little bit more elaborate picture of this would be that let's say the points in this region represents the domain of G. Okay. And let's say the points here represents the range of G. Okay. and the domain of f, let's say, is this. That's the domain of f. And of course then you have the range of f. Is everybody clear what I mean by the range of G and the domain of f? Okay. So notice that the domain of f and the range of f, they have a common area, right? So those are the common values in the two sets. Now, what's happening with the composition is that you start with an x in the domain of G, and then you're applying G to that x. You end up with a y in the domain of f, in the range of G as well as in the domain of f. And if y is not in the domain of f, you cannot apply f to it, right? So, and then you are applying f in order to get another value z, and z lies in the range of f. Okay? And the composition f circle G is basically taking x all the way up to z. The question is, so notice that if I start out with a point in the domain of G, and then if I end up with a point in the range of G, however, that point is not in the domain of f, then I cannot apply f to it anymore, right? Is that okay? If I start with a point in the domain of G, but when I apply G, I get a point in the range of G, but it's not in the domain of f, then you cannot apply f to it, right? Yeah.
So then there's no solution effect, it's like a composition effect?
Well, it means that this point will not be in the domain of the composition. So what I'm trying to get at is, what's the domain of the composition function? So the domain of the composition function, what is that? Well, notice that when you're computing the f of g of x, you're applying g to x first, right? So x has to be in the domain of g first, right? Is that okay? So when you are computing the composition of f and g, you're applying g first to the inner function. Therefore, x has to be in the domain of g. So the domain of the composition is all values of x inside the domain of G, such that the corresponding value of the values of G of x is in the domain of what? The domain of f. The domain of the composition is all values of x for which G of x is in the domain of f. Right, because whatever x you have, you're applying G first, so x has to be in the domain of G, but then you're applying f to G of x, so G of x has to be in the domain of f. Otherwise, you cannot apply f. Okay, so in the domain of G, you pick all values of x for which G of x is in the domain of f. That would be the domain of the composition. So basically, maybe let's say that here is a breakup of the domain of f, and this green side is the domain of the composition. That is, all the values of x in the green region will be mapped into the region right here, let's say. And then that region is in the domain of f, and now you can apply f to it. Okay? So this green region would be the domain of f circle G. I think the best thing to do is do some examples and explain that. Let's take a easy example first. Let's take f of x is x squared plus 1, g of x is x minus 3. then what is the composition of f and g at x? Well, it is given by f of g of x. So what is g of x? G of x is x minus 3, so I have f of x minus 3. And then I have to compute f of x minus 3. So how do I compute that? Well, I look at the formula for f. It says that what is the output value for the input x? Well, you square the input plus 1. So in this case, the input is x minus 3, so you square the input x minus 3, and then you add 1 to it. That's the value of f of x. So the composition function is given by x minus 3 squared plus 1. Now, in this case, can someone tell me what's the domain of f? What's the domain of f? All real numbers. And what's the domain of g? It'll be all real numbers as well, right? And what's the domain of the composition function? Yeah, it'll be everything inside the domain of g for which the value of g of x is in the domain of f. Because the domain of f is everything, the domain of f circle g would be everything here. Right? Okay, so that's that. Let's look at another example. Last time I gave you an example where I computed f circle g and g circle f, and we saw that they were not same. They were not the same. And so f circle g and g circle f, generally they are unequal, right? They are not the same. Okay, so another example. Let's say I take the function f of x to be 1 over x minus 1, and I take the function g of x to be 1 over x. Now, in this case, what is this composition of f and g? Well, it will be f of g of x. And what is that equal to? Well, it is f of 1 over x. And what is f of 1 over x? Well, I go to the formula for f. I replace x by 1 over x. What do I get? 1 over 1 divided by x minus 1. And then, how do I simplify this? You can multiply by multiply and divide by x, or you can just say that the fraction below the common denominator is x, and then you are subtracting something, so you get 1 minus x like this, right? You agree with that? And so finally, I could say that f circle g evaluated at x is x divided by 1 minus x. Is that okay? Now let's look at the domains. What's the domain of f? Domain of f is everything except what? Everything except 1, right? Because you have x minus 1 in the denominator. What's the domain of g? Everything but 0. What's the domain of f circle g? What is the domain of f circle g? Everything except 1 and 0. You guys see why? First of all, if I only look at this formula for the composition, right, then I see that the domain should be what? Everything but 1, right? However, because you are defining the composition as the composition of f and g, remember you applied g first, right? However, you cannot evaluate g at 0, right? So always remember that the domain of the composition, it would be everything, will be the domain of G, will be the domain of G, and then from the domain of G, let me say it this way, sorry. So it will be the domain, everything in the domain of G, such that G of x is in the domain of f, right? In other words, you take everything in G and exclude the values of x for which G of x is not in the domain of f, right? So you take everything in the domain of G and get rid of the values of x for which G of x is not in the domain of f. And what is that? Well, it means from the domain of G, get rid of the values of x for which G of x is what? 1. Because if G of x is 1, you cannot apply f to it. Okay? And we know that the domain of G is everything but 0. And I think G of x would be 1 when x is what? G of x is 1 when x is exactly 1, right? Because G of x is 1 over x. So G of x would be 1 for what x? So I get rid of just 1, right? From the domain of G, I get rid of 1. So what do I get? I get everything except for 0 and 1. So negative infinity to 0, 0 to 1, 1 to infinity. You agree with that? Now you might say that, hey, you got a formula for f circle G, which is x over 1 minus x, and the domain of that function can be taken to be everything but 1. That's true. The domain of this guy is everything but 1. However, we came to that by defining f circle G. So because it's a composition, the domain would be given by the other one. Is that making sense? The composition is equal to that as long as x is not 0 or 1. Is this making sense? Okay. All right. So usually you don't have to worry that much about this, but you should be aware of this in principle. Okay. Okay. Let's do another example. Suppose that I have two functions with finite domains. So let's say the first row gives you the values of the domain 1, 2, 3, 4, and the second row gives you the values of the function f. Let's say it is 2, 3, 4, and 5, and the third row gives you the values of g of x, and let's say it is 1, 3, 3, 4. Okay. So then, if I ask you, hey, what's the value of the composition of f and g at let's say 2? What would you say? Well, you're going to apply G first, right? So if you apply G to 2, what do you get? 3. And then you're going to apply F to it. So if you apply F to 3, you get? You see that the answer is 4? Again, this means what? You're applying G of 2 first, and then you're applying F to that, right? What is G of 2? G of 2 is 3, right? And then F of 3 is 4, right? Is that making sense? So in your exercises, you'll see that there is one problem where you're given a table like this and you're asked to compute the composition function at different values of x. Any questions on that? Another example. We can also take the composition of more than two functions, okay? So if we write, let me start with if I take the composition of f and g first, and then take the composition with another function h, that's the same as f composition with g composition with h. So I can take the composition of g and h first and then take the composition with f, or I can take the composition of f and g first and then take the composition with h. They are the same. Okay? So if I write just f circle g circle h, right? If I write this function, I mean one of this, okay? Does that make sense? That symbol f circle g circle h means one of the two. Okay? So let's do an example where first of all, so then what would that be? What's the meaning of this composition? Well, it is f of g of h of x. How many parentheses do I need? One more. Okay? If you have 4, 5, 6, you can have as many as you can imagine. So this is the definition of composition of three functions. So for example, let's take f of x be x squared, g of x be x plus 1, h of x be root of x. Okay, then what is f circle g circle h of x? Okay, again it is f of g of h of x, and well, what is h of x? H of x is root x. Now I have to apply g to it, so I get f of what? Root x plus 1 when I apply g, and finally I have to apply f to it, and when I apply f to it I basically square it, right? So it will be root x plus 1 whole squared. So that's the composition of those three functions. Is everyone okay with what we did so far? Any questions, anyone? Any questions at all? No? Okay, so let's review some facts about polynomials now. So, polynomials. Okay, so what are polynomials? A polynomial is an expression of the form an x to the n plus an minus 1 x to the n minus 1 plus dot 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 plus a2 x to the 2 plus a1 x plus a0, where n is a positive integer, or it could be, I should say it's a non-negative 0, so or it could be 0, and a0, a1, dot 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 up to an, these are real numbers. So these are constant numbers. So for us, a polynomial would be anything of this form. So what does it mean? It means that you basically have non-negative integer powers of x multiplied with certain coefficients and added together, right? Okay. And well, what would be some examples of this? Well, some examples of this would be, you can make up anything you want. Half x to the 5 plus 3x to the 4 plus 7x to the cubed minus x squared plus 7x plus 2. That's a polynomial, right? And also, if I have x squared plus 1, that's a polynomial as well. You might say you don't have a x to the 1 power there, right? You realize that? So x squared plus 1, for example, that's the same. That's the same as x squared plus 0 times x plus 1. Okay. So that's a polynomial as well, and you can write down many other examples of polynomials. So again, did that make sense? So you have non-negative integer powers of x multiplied with certain constants and added together, right? That's a polynomial. If you have a polynomial, what's the degree of the polynomial? What's the degree of a polynomial? Yeah. No, it's the largest exponent that appears in the polynomial. Okay, so in this form that I have, the degree. Let me actually call, if you don't mind, call this p of x. Let me call this expression p of x. Then the degree of this polynomial p is n, as long as an is not 0, of course, right? So it's the largest exponent that appears in the polynomial. For example, what's the degree of this polynomial here? The degree of this guy is 5. The degree of this guy is 2. Okay, and also when you have a polynomial, the coefficient of the largest exponent, largest power of x, is called the leading coefficient. So this guy here, that's called the leading coefficient. Leading coefficient. And this a0 here, that's called the constant term. Is everybody okay with that? These are just terminologies. Now, suppose I give you a constant like 5. Is 5 a polynomial? Can I view 5 as a polynomial? In fact, I can, because look at my definition. My definition for a polynomial is any expression of this form here, right? Now, I didn't say anywhere that a1 up to an, they are non-zero, right? I didn't say that. So what if all the coefficients are 0 from a1 up to an? If all these coefficients are 0, you're left with the constant term, right? Am I making sense? So constants are also polynomials. So here are some terminologies that we have special names for polynomials. So for example, if I just have a constant, right, this is called a constant polynomials. Constant polynomials. And if I have a polynomial with degree 1, if I have a degree 1 polynomial, right, this has degree 1, those are called linear polynomials. Can someone tell me why they are called linear polynomials? Their graphs are linear lines. And then I have ax squared plus bx plus c. So any time I have a polynomial of degree 2, it's a quadratic, very good, quadratic. And if I have, let me write down one more, ax cubed plus bx squared plus cx plus d. This is a degree 3 polynomial and it's cubic polynomial. Is everybody okay with that? Okay, so and you can give other names, but I think you get the idea. So there are a couple of facts that we want to before I forget, monomials are just special names for these simpler polynomials. Just 1 power of x. So those are called monomials. Yeah. So these are these are the simpler polynomials. Yeah. So they are also polynomials. Yes. Mono simply means just one term. So, yeah. Okay, so there are some facts about polynomials that we need to remember. First of all, let me remind you the definition of a root for a function. So if I have a number alpha, alpha is a root of a function f of x if f of alpha is equal to 0. So alpha is a root, or sometimes people use the word 0, okay? Alpha is a root or a 0 of a function f if f of alpha is 0. In other words, if you look at the graph of f, alpha is what? Where it crosses the x-axis, which is the x-intercept. Yes. Okay. So here's one fact that you want to remember about polynomials. Alpha is a root of a polynomial p if and only if. You guys are familiar with IFF? It means if and only if. If and only if x minus alpha is a factor of p of x. What does it mean to say that x minus alpha is a factor of p of x? No. So x minus alpha is a factor means x minus alpha divides the polynomial. So if you divide the polynomial by x minus alpha, the remainder would be 0. In other words, when you can write the polynomial p as x minus alpha multiplied with another polynomial q, where, what can you say about the degree of q? Degree of q would be what? Exactly 1 less than the degree of p. Degree of p minus 1. Is that making sense? So it's like saying that 2 divides 6, right? 2 divides 6 means 6 is a multiple of 2, right? When we say 2 divides 6 or 2 is a factor of 6, it means that 6 is a multiple of 2. 6 is 2 times 3. So same way, if I say x minus alpha is a factor of p, it means that p is a multiple of x minus alpha. In other words, p is x minus alpha multiplied with another polynomial of lower degree. Is that making sense? Okay. Let me give you an example to explain this. Let's take, so here's an example. Let's take the polynomial p of x to be x cubed plus 3x squared plus 3x plus 1. Notice p of negative 1 is what? What is p of negative 1? What's that? P of negative 1 is 0, right? Because you get negative 1 plus 3 minus 3 plus 1, right? Do you agree with that? So p of negative 1 is 0, so that implies negative 1 is a root of p. Okay, so then x minus that root, which is the same as x plus 1, is a factor of p of x, which means that p of x can be factored out. P of x can be factored out as x plus 1 multiplied with some q of x, where the degree of q would be what? 2. It's a quadratic polynomial. But the question is, how do you find that q? What's that? Long division. You just divide out x cubed plus 3x squared plus 3x plus 1, and you simply divide it by x plus 1. Well, how do you divide it? Well, you have to match x cubed, so you multiply by what? X squared. So you get x squared here. Subtract, you get 2x squared plus 3x plus 1. And then you multiply by what? 2x. You get 2x squared plus 2x. And then you get x plus 1. Multiply by 1, you get x plus 1. The remainder is 0. So that tells you that if I have x cubed plus 3x squared plus 3x plus 1, that's the same as x plus 1 multiplied by the quotient, which is x squared plus 2x plus 1. Is everybody okay? Of course, x squared plus 2x plus 1, you can factor that out more, but that was not the point of this example. I was just illustrating the fact that if you have a root, then x minus the root is a factor. It means that you can factor out the polynomial where one of the factors would be x minus the root. Okay. Any questions so far? Yeah, if you want to, yes. Yeah, I mean, we probably won't do it much, but yes, you can. Okay, so what I want to look at now are the monomials. So remember, the monomials are 1 x x squared, x cubed, actually 4, actually 5, actually 6, and so on. We know the graph of 1, right? What's the graph of 1? That's just a horizontal line with height 1. The graph of x is just the straight line, where it makes a 45-degree angle with the positive x-axis. And the graph of x squared is a parabola, right? But how about the graphs of the other powers of x? Just these simpler functions. Well, yeah, so what happens is that the graph of even powers of x, starting from x squared, the graph of even powers of x, they all have the same shape, okay? That is, they all look like a parabola. The graph of x, you know the graph of x cubed, right? And the graph of odd powers of x, like actually 5, actually 7, they all have the same shape as well, okay? So, but compared to each other, let's see how they look like. So, first of all, what I want to do is look at compare the two functions, x squared and x to the 4. Okay, I want to compare these two functions. Now, if I have that x is between -1 and 1, if x is between -1 and 1, notice. Notice that means which function would be bigger, x squared or x to the 4? When x is between, think about the number 0.5, right? 0.5. Which one is bigger, 0.5 squared or 0.5 to the 4? 0.5 to squared is bigger one, right? So when x is here, then in fact x to the 4 is smaller than x squared, right? You agree with that? 0.5 squared is what? 0.25, right? So if you take this fourth power, you get 0.020625. So when x is between -1 and 1, x to the 4 is smaller than x squared. However, when x is to the left of -1 or x is to the right of -1, what happens then? Then x to the 4 is larger than x squared. Right? Like, for example, something bigger than 1 would be 2. 2 squared is smaller than 2 to the 4. Same way, if I take -2, for example, -2 to the 4 is bigger than -2 squared. Okay, so then, so let's look at the graphs of x squared and x to the 4 then. Okay, so let's say this is my x-axis and this is my y-axis. The graph of the parabola x squared looks like what? Well, let me see if I can make a nice enough graph. Okay, so let's say this is the graph of x squared. So then what's the graph of x to the 4? Well, let's say this is the point where I have -1 here. This is the point where I have +1. Let me use red. What would be the graph of x to the 4? Well, between -1 and 1, x to the 4 should be below x squared, right? Because x to the 4 is smaller. Outside of -1 and 1, x to the 4 is bigger, so it should be above x squared. So that means the graph would be something like it should be below the green curve between -1 and 1, and after that it goes up, right? So it goes up after that. So the red one would be the graph of x to the 4th. Is everybody okay with that? What would be the graph of x to the 6th? Same shape, except that it will be between -1 and 1, it will be below x to the 4. Outside of -1 and 1, it will be above x to the 4, right? And so on for x to the 8 and x to the 10 and so on. Is everybody okay with that? And you can say the same thing for the odd powers of x. So let me end by saying how actually. So let me make my x-axis, y-axis. Okay, so the graph of x cubed looks like what? The graph of x cubed looks like something like this. So let's say the green one is the graph of x cubed, and let's say here is -1, and here is -1, let's say here, +1 right here. And what would be the graph of x to the 5, for example? So x to the 5 will look like this. After this point, it will be like this, coming back. Is everybody okay with that? So that's how the x to the 5 will look like. Any questions on that? Okay, so this will be it, since this is where I ended in the other class. So on Wednesday I will finish all the sections up to 1.4, okay?
Yeah.